Casey, what do you know about Emergy?
Nothing.
Nothing? You ever heard of it?
No.
You heard of H.T. Odom?
Yes.
You know who Dr. Brown is? Mark Brown?
Yeah.
Matt Cohen?
Yeah.
Matt Cohen did his dissertation under H.T.
Okay.
And it was on Emergy, but it was the Emergy like soils.
Okay.
Let's talk about that after.
This is so a recap of the PhD. This is a recap of the PhD dissertation of myself, Chris. It's called The Evaluation of the Energy Sources of Earth's Geobiosphere and the Emergy of the Crust. So I'm re-recording it now because the actual defense I forgot to screen capture, or I didn't forget, but I clicked it and I guess I didn't click it. I didn't make sure it clicked. And I did a Facebook Live of it, but it was like 2 hours and 50 minutes. So not going to post a 3-hour video. So this should take about 30 minutes. And if they have any questions, this is Paula and Casey. If they have any questions, we'll answer that too. But other than that, I mean, this is like, Emergy is a really broad perspective on environmental accounting, is what it is. And so everything can be measured with Emergy. Kind of like, almost like the law of frequency. Like everything in the universe has a vibration. It has a specific frequency. Every atom, every person, every personality, every emotion, everything has Emergy. Mm-hmm. If it had zero Emergy, it basically wouldn't exist. It's kind of like a absolute zero. Everything has temperature, and even as you approach absolute zero, it doesn't happen. Funny things happen when you get close to absolute zero. So everything has Emergy. It's like the memory of evolution. It's a quantitative measure of what it took to evolve something, either an organism or a technology or an idea. And it gets a little abstract when you start trying to measure ideas, but it's a relatively new science. It's like 30 or 40 years old. Mm-hmm. So what I focused on, actually I'll go through why I'm focusing on what I'm focusing on. And so this is the definition I'm using. It's not Odom's definition. It's this guy that I went to in Italy to study with. His name is Corrado Giannantoni. And he was a, what do you call it? I guess a nuclear physicist that is now more focusing on like mathematics. And anyway, so his wording, like most physicists and mathematicians, are very like detailed, precise. And so I like this definition. Emergy is the dissipated potential energy of one form from a predefined time origin needed to produce a given system under consideration. So how much potential energy dissipated to make something from given a time window that you have to define. So the outline is going to be objectives. Then I'm going to go into the chapters, which were radioisotopes, the budget of the Earth, the Emergy budget of the Earth, the crust, how much energy it takes to produce minerals that we use, like silver, like you were just talking about, and then outlook for the future and the specific outcomes from my research. So the order of thought, so this is what I was about to go into. So I did my master's degree, I was an industrial engineering major, and then I got my master's in industrial engineering at University of Oklahoma. And about halfway through my master's, my advisor, I was searching, I was looking for I was modeling population trends in the U.S., and he asked me to look into net energy of wind and nuclear. And so I found a paper by H.T. Odom that was explaining how wind is generated, where the sun just heats up the atmosphere and then the atmosphere churns up and then you get wind. And it just blew my mind. It's so simple. How did I not know this? And it was just a series of realizations like that. It was very understandable explanation of just how the natural world works. And he seemed to be explaining kind of general principles behind everything that it was just really appealing. It gave me gratification. So I changed my focus into, I did an Emergy evaluation of a hybrid vehicle compared to a internal combustion. So I did a Corolla versus a Prius. And because they're more or less the same car, the mass is the same, everything's about the same, just a different combustion or a propulsion system. And the results of that they were basically the same. There was a little bit difference for the big batteries for a hybrid, but there was also more gas use for the other one. And when you put it all into Emergy terms, it was basically the same. Surprisingly, actually, the biggest contributor was the Emergy of driving. So the Emergy of supporting a human, the food and everything it takes to grow you, and then you put that time into driving. That was the biggest input. So if you took that out, because it's like the same time for each car, then the next biggest input was actually the materials. But the emergy of materials, so this is where we get into the crustal emergy. The emergy of the materials was highly vague. Like everything else in emergy, except for the nuclear emergy. But everything else like fossil fuels, lumber, natural resources like wind and solar, those are actually pretty well defined. They're pretty vetted, and like science can accept how we do those. But the minerals, the crustal minerals, were just like hugely vague. It was like if it's twice as concentrated, so if you have like a 20% ore deposit, if it's a 40% ore deposit, it's twice as much energy. That's how they would do it. If it's 60%, it's 3 times as much energy. And it's like, why is it just 3 times more energy? Just because it's 3 times more concentrated. So I started looking into the thermodynamics of the crust. From that, it was like crust is a huge mass that is generated over billions of years. So it kind of, that broad time and space scale got me looking at the whole planet. How has the energy of the planet been changing? And then I came to the realization that there's no energy for nuclear fuels, like uranium, or like if you have potassium in the crust, a lot of the heat that we get from Earth heat is from the radio decay of potassium. So we had no energy of nuclear, nuclear decay. So when you combined all that, I was like, well, this is all theory. Like I'm just doing a theory paper basically, which is fine, but who cares outside of the Emergy community? Like, if I told a soil scientist, hey, I did the Emergy of nuclear fuels, he'd be like, I don't care. But if I say I just did an environmental accounting of the U.S. economy, and I can tell you like how much nature supports a dollar, like what is that? So we can actually measure the dollar value of a tree, something in a way that's other than how much are you willing to pay for that tree. But I can say how much energy it took to make the tree, and what's that conversion to a dollar, based on the energy to dollar ratio. So if I have an economy that has $15 trillion, like the U.S. economy, and it has so much energy it takes to churn that money. We use natural resources, and that's what churns the economy. I can make a ratio and say there's this much energy per dollar. And so then I say there's this much energy in a computer, I can convert that to dollars. So it's different. Because traditional economics is how much would you pay for that?
Yeah, the price doesn't reflect.
And right, and it will fluctuate depending on supply and demand, and if you really need a computer versus you already have one. But the energy value won't change. Only as evolution, things become more efficient, so you can make it with less energy, but that's really slow. So the energy value is constant. It's not subject to your opinion. How much would you pay for it? So that's the power of it. Okay, so up until now, there was no energy of radioisotopes, so we just didn't account it. We just didn't, if we mine uranium from the crust and it's used in nuclear, 20% of U.S. electricity is made from nuclear power. But we weren't counting that. And then gravity drives the fusion process. So basically that chapter is the stellar nucleosynthesis, which basically means that the sun was a big dust cloud and gravity pulled it all together, and when it got dense enough, it got hot enough, and then fusion happened. So particles were colliding, eventually they smashed them together, hydrogens became heliums, and so on. That releases a bunch of energy, which we call sunlight, and also in really massive stars, the process gets bigger and bigger and bigger, and you start making heavy elements like iron and uranium and things like that. So gravity drove it all. Gravity is what produced it. There's a thing, and I know you girls might not be interested in all of this, but I gotta say it because it's part of this. There's something called neutrinos. We don't count neutrinos because we don't know how to use them. Basically, neutrinos just pass through mass and matter. Neutrinos pass through the Earth at the speed of light, and it doesn't even hit anything. And so they're kind of useless, and it's a small amount of energy, so we just don't count it. And there's another thing called mass defect. So this is the mass lost. Let's say it takes 56 hydrogens, or 56 hydrogens to make a nickel. Actually, the mass of the 56 hydrogens is more than the nickel because it loses mass as things fuse together. That mass becomes sunlight, according to Einstein's equation of mass equals energy. But we don't know how to account the energy of that mass, because then we would have to say how much energy is in a proton. And, well, what did it take to make a proton? That goes back to the Big Bang. Big Bang, the universe expanded, it cooled. As it cooled, protons were formed from quarks. So it's kind of a precipitation process, or not a condensation process. And the understanding of what science understands about what happened then, it just gets hella vague. And so we discount, we don't count mass defect, the emergy of mass defect. We count the mass defect, we just don't count the emergy of it. So we assume gravity is, it's actually the thermal energy is what collides the elements together inside of the sun. But that all comes from gravity. Thermal energy is kinetic energy at a microscopic scale. And kinetic energy and gravitational potential energy are the same thing, it's just a reference. Gravitational, it's the only two forms of energy that can be converted into the other without any loss of heat. In any other process, as you convert energy to something else, you lose a little bit according to the law of entropy. But when gravitational potential energy becomes kinetic energy, you lose nothing. It's 100% conversion because it's a reference frame according to Einstein. So we just use the kinetic energy, the translational kinetic energy specifically, and you can look in the document for the actual proof of this. The translational kinetic energy is the gravitational exergy. Exergy is a fancy word for potential energy. There's the equation for it. So this is how we say thermal energy. What is the temperature at the fusion process? Well, that's how many gravitational joules it took to make that fusion happen. So this is what's called the PP1 and PP2 cycles. This is what makes sunlight in the sun. PP1 is just proton is what PP stands for. So a bunch of protons smashed together and make a helium, or in the bottom diagram, a bunch of protons smashed together with an already made helium to make 2 helium. And this emits some sunlight. When we average, according to these two processes, one occurs at like 14% in the sun, the other one's 86%. So we'll do a weighted average of how much these occur in the sun. And this is the transformitie, how much gravity it takes to make a joule of sunlight. And you'll notice that it's below 1. It's less than 1. It's times 10 to the negative 4. So this is 0.0007 joules of sunlight makes a joule, or joules of gravity makes a joule of sunlight. So that's something like 13,000% efficiency, which is ridiculous. That's like saying for every joule, you make 13,000 joules. Well, where did the extra come from? That's because we're not counting mass defect. So if we counted mass defect, that would be different, but we have to make massive assumptions for mass defect that are not falsifiable. So we don't do that. And we'll see how this preliminary assumption trickles down into the final result. So we do the same process. I don't have all the diagrams here. You can look in the document. The same process for the heavy isotopes. And then we do a ratio of the two. So how much gravitational energy it took to make a uranium, how much gravitational energy it took to make sunlight, and the ratio of the two is the equivalence. So how much sunlight is equivalent to uranium? How much sunlight is equivalent to potassium? How much sunlight is equivalent to thorium? And that's where we get this solar equivalent joule, which is SEJ. Solar equivalent joule per joule of radioisotope. And if at any time you have a question, if you haven't totally spaced out, totally just be like, hey, I have a question. So there's a diagram of potassium. I guess I lied. Here is a diagram of... So it's just a bunch of fusion processes. And then you account for the temperature of each of these fusion processes and add it up for the final result of potassium. Then potassium has a decay energy, so it will decay to a stable isotope, and the energy released in that decay process is the numerator in a transformity. So how much potential energy, that's the numerator. How much emergy to make it, the denominator. Sorry, I got it reversed. How much emergy is the numerator, and how much energy is released in decay is the denominator. The ratio of the two is the transformity. The reason why transformity is important is because we can make a transformity for everything. Everything that has emergy has potential energy. You have potential energy. If you have no potential energy, you have no emergy. So everything has potential energy. You can burn this rug, it has potential energy. You eat this food, it has calories, that's potential energy. My voice is sending sound energy, that's potential energy. So if we can make a transformity of everything, something very interesting happens. When you place everything conceivable and you get the transformity of it, you start to see patterns. The things that took more energy to make have higher transformities. And so it's called quality. So there's a spectrum of quality. Sunlight is the lowest quality. It takes 1 joule to make 1 joule. And then you have things like information that take a lot of energy. Electricity, fossil fuels, rain, wind, waves, sunlight. Okay. And then we do the same thing for peak iron. Peak iron is the preliminary for all the heavy isotopes. Iron happens, a supernova explosion occurs, a bunch of alpha particles, which is a helium nucleus. So you have an iron, and then a bunch of alpha particles smash into it in a few seconds and make it a uranium. So we do the accounting of that, and there's the transformitie of it. So the hypothesis, you might say, would be that as an element gets heavier, it takes more energy to make it. And so its transformitie should go up. And we found the opposite, actually. That as the element gets heavier, its transformitie goes down. And the reason for this is because the heavier the isotope, the more potential energy it has. Uranium has a massive potential energy. As it decays down to lead, it releases a lot of energy. Potassium doesn't really have that much energy it releases when it decays. And so an interesting hypothesis to test would be to fill in all the missing ones. I mean, we just skipped from atomic mass 40 to atomic mass 232. So there's a whole bunch of things going on in between there that I wonder if this trend would continue. If it's a smooth trend that as the element gets heavier, the transformitie gets lower. That could be investigated. Just apply this method and get the data. So let's see, anything else I need to say about this? And again, we can equate it all to sunlight, so we get a solar equivalent joule. That's important because gravitational energy is kind of a universal unit. It's something to use in the cosmic scale. When we get down to measuring things on Earth, we want things in sunlight, in terms of sunlight. It does us no good to think of what's the gravity around Jupiter's rings or something. That's way far away. Okay, so the third chapter. The GEB, which is an acronym for the Geobiosphere Emergy Baseline. How much energy drives the geobiosphere? So there's some realizations that occurred that this needed to be overhauled. Is that sunlight doesn't make the tides. So there's basically three inputs that were going into my dissertation. It was considered three independent inputs to the planet. Sunlight, tides, and earth heat. So there's a realization that came from a friend of mine, Marco Rauji, that sunlight doesn't make the tides. Tides are independent. And sunlight doesn't make the deep earth heat. Deep earth heat happens whether the sun shines or not. So it's not appropriate to call Emergy, like to say that there's an Emergy of deep earth heat. It didn't make it. It's independent. Then, so I add the nuclear UEVs also. The nuclear UEV is an acronym for unit energy value. So I'm also combining nuclear. So I'm actually saying there's four independent things now. Sunlight, tides, and then the deep heat is separated into, there's this heat from the Earth forming. It collapsed on itself. It's called relic heat. So the Earth is still hot because it collapsed on itself. And then there's nuclear material inside the Earth that's, as it decays, it heats up the Earth. So those are two independent sources. So there's four independent sources to the baseline of the planet. And it's actually the tides. Well, I'll get into that in the next slide, how the tides are made. So four independent energy sources, and we express them all in terms of gravitational energy now, because there's solar energy. They weren't made by sunlight. So that's why we needed to make everything in terms of gravity. Sorry, I got a nose itch. Keep picking my nose almost. But technically, it's not energy. It's equivalent energy. We're expressing everything in terms of solar equivalent joules. When you add them together, it's still solar equivalent joules. So it's kind of inappropriate to call it the Geobiosphere Emergy Baseline. It's the Geobiosphere Equivalence Baseline. I actually vote for calling it the Planetary Baseline. I like that word, that wording. But, you know, in some cases, like when it comes to nomenclature, science is a democracy. And so, even if I don't agree with science being a democracy, everybody votes. We're going to call it the GEB. I want it to be the PB. Also, I like peanut butter. So, the concept. You express all these four independents, the deep earth heat, the radionuclides, the sunlight, and the tides, how much gravity it takes to make them. Great. Then you express them all in sunlight. You make an equivalence, because there's gravity per sunlight, gravity per radionuclides. You can say, well, then there's sunlight per radionuclides. There's sunlight per deep heat. Then you add them all together, and you say the solar equivalent joules of the planet. So we start with the accretion. There's a binding energy. How much? This is cosmic geodynamics or planetary physics, and this is Newtonian physics. We were just talking about Newton. And Odom is like the modern Newton. Odom's the guy that created. If you're watching this later, you don't know who H.T. Odom is. That's my academic grandfather. My academic father, my advisor, is Mark Brown, who is the protege and successor to H.T. Odom. And anyway, little known fact there. So the binding energy is how much energy it took to make the Earth. If you separate all the material to infinity in every direction, that potential energy is the binding energy. And it's expressed more or less by this equation there. The equation is more complicated than that because the density of the Earth is not uniform. It gets denser as you go deeper. But it's close to that. And there's a reference for it if you look in the document. So it's that much energy binds the Earth together. And then you have the Earth is rotating around its central axis. And then you have the moon orbiting around it. Now the theory goes that the moon used to be part of the Earth. And a big rock hit the Earth 4 billion years ago or something, 4.5 billion years ago, and it ejected all this material into space that became the moon. But at one point, all that material was together, and there's a principle called the conservation of angular momentum. So I backtracked, back-calculated what's using the modern angular momentum of the Earth-Moon system. It's conserved, so you go backwards in time, you can figure out what the rotational kinetic energy of the Earth was. It was spinning faster, basically. So you go back in time, the moon gets closer, the Earth spins faster. When the dinosaurs were around, the day was 19 hours. When the Earth formed, the day was 4.5 hours. And then heat is the same thing. We have a heat record for about 3 billion years, and then we have to kind of guess going back. When I say we, that is a we, because I use other scientists' data. I didn't go out and measure the heat of the Earth. And so, but I have a rough approximation of the original heat content and the original kinetic energy of Earth's rotation. And all of that formed from the binding energy. The Earth collapsed on itself, it started to spin more. The Earth collapsed on itself, it generated the heat. So I have the progenitor and then the products. And there's a diagram for it. So you have this geopotential energy symbol that interacts with dispersed matter that doesn't have any potential energy. And it creates kinetic energy and heat. A storage of kinetic energy and a storage of heat. But then how do I say, well, how much potential energy went into heat and how much went into kinetic energy? This is the part where I might lose you guys. This is highly theoretical. This part, if I haven't already lost you, I know I talk fast. And take a breath. If you don't know, I'm a yoga instructor. And so, I go into details in the paper. I'll just give a very cursory overview right now. There's different allocation procedures in Emergy algebra. One of the most highly suspect features of Emergy is that Emergy is not conservative. So, if I add the Emergy of products, I might get more Emergy than what was used to create them. I was working to eliminate that rule. But, c'est la vie. And so these are the options. You have byproducts, split, and coproducts. A byproduct means that we have an efficiency. We know how much, what the heat loss is in generating kinetic energy, what the heat loss is in generating a storage of heat. We don't have those quantities. That's at the origination of the Earth. We don't know what the efficiency of conversion is. You know, when you make electricity in an electric generator, you know what the efficiency is. When you burn coal and you make electricity, you know how much is lost to heat. You know, if I eat food and I get on a treadmill and I generate energy, I burn a certain number of calories. But I only create a certain kinetic energy as I run. There's an inefficiency there, there's a heat loss. So we're looking for the heat loss and how much it took from the binding energy to make kinetic energy and how much it took to make Earth heat. We don't know that number, so we have to make estimates. The other options would be coproduct, which would be like, I don't know, we just throw our hands up and say all the potential energy made both products. So that doubles the energy. We're saying it all made the kinetic energy and it all made the deep heat. And later when we add them together, We just take the largest of the two, which of course they're equal. But in some smaller scale evaluation, if we do like a coral reef system, like I'm about to show, it has some tides, it has some deep heat. We don't add the energy of the both together if they're co-products. So it makes every evaluation cumbersome if we have to say, well, which one is larger? So we avoid that. A split, even though it's not ideal, it takes away any bias. A split means that we just say it's proportional to both. So if we have 10 units of kinetic energy and 1 unit of heat, then for every for every unit of binding energy, 10 parts go to kinetic energy and 1 part goes to heat. It's proportional. So their transformities end up being equal because they're proportional, which is weird because their transformities should be different. We know that tides are different than kinetic energy. Their transformities should be different. But it takes any subjectivity out of it. So that's the one I end up going with. In the publication that went into environmental engineering, I think, is where the paper went. We took a weighted average of 3 of these methods. I disagree with that, but it's a democracy. So in my dissertation, I take my preferred one, and I'll explain exactly why I do that here in a second. So these are some of the numbers. I hate tables that have so many numbers you never know what to look at, so here I'm highlighting it. The final answer, what is the planetary baseline, is the sum of the Emergy of all 4 sources. So that's 13.9 E24. It's a really big number. It used to be 15.2 E24. Originally it was 9 E24. So it's still around that ballpark. What is that, quadrillion or something? These are transformities. You can look at it yourself. These are transformities of the deep heat, radiogenic heat, and the tidal dissipation. That transformity of radiogenic heat there is a weighted average of the 4 main isotopes I looked at: potassium, 2 kinds of uranium, and thorium. And then if you group the radiogenic transformity with the deep heat transformity, you can just get a generalized geothermal transformity. Because a lot of times when you do a land area analysis, really important when you're looking at like sediments. So I want to look at the Emergy of diatomite or something, and that was kind of pressed together 100 or 200 meters below the surface out in the desert underneath what used to be lake beds. There's some deep heat there, but we don't know how much of that deep heat was radiogenic and how much was relic. So we just say it's geothermal. Well, so we need a transformity for that. So we take a weighted average of geothermal of relic heat and radioisotope heat. So there it is right there, 8,240. And then a comparison. So this is why I chose the split, because ultimately my number, this 13.9, is not going to be used in the future. 2 other people, Dr. Brown and Sergio Uggiati, and then Dan Campbell made another publication. They do the original method, which was back calculation. Brown and Uggiati specifically did the original method. Campbell comes up with a new method, but I'm not going to go into why I disagree with some things. Probably he disagrees with everything I did. So, we just disagree. But anyway, what's interesting is I do forward calculation, which means I go and say gravity produced everything, and I go forward from there. Their backward calculation method says that, Campbell did something with the lithospheric drift, so the entire lithosphere of the Earth is kind of sliding over top of the mantle. So he calculates the kinetic energy of that because the moon is kind of dragging the whole shell over the molten magma. Brown and Uggiati say, it's a bunch of relationships for, the sun and the deep heat generates the tides, and the deep heat generates crustal cycling, things like that. You got to look at their papers. But they're saying, look at the relative occurrence of these Earth phenomena. Let's just relate all the sources together. Mine is there's gravity that produced everything, and let's go forward from there. So mine's forward calculation, theirs is backward calculation. And all the answers are pretty similar. Keep in mind, though, that I don't account for mass defect. If I accounted for mass defect in the nuclear transformities, my baseline would be about 3.6 instead of 13.9. It'd be like 3.8. I'm sorry, it'd be about 3.85. The Emergy of deep heat, of relic heat, and the Emergy of tides would be insignificant. They would be so small, and the Emergy of radiogenic heat would be noticeable. It'd be notable. It'd be 0.2 out of 3.8. Sunlight would dominate everything. The Emergy of sunlight's the only one that would be important if I accounted for mass defect. The Emergy of mass defect. So that really raises a question. It raises an eyebrow. because the biggest reason that validates Campbell and Uggiati's use of their baseline is that my forward calculation method produces a very similar result. So it all seems okay. But we're not accounting mass defect. So that really needs to be looked at. The Emergy of mass defect, how can I include it? And actually, I would propose a wholly different method. I would say, what's the gravitational potential energy that's lost in a star? So like the sun will end up being a white dwarf, eventually a brown dwarf. Right, brown dwarf. It won't be a white dwarf, it'll be a brown dwarf. I forget now what kind of dwarf. It becomes a dwarf. And so that has a binding energy because it has a specific radius. You know, the supernova, we're assuming it doesn't become a black hole, will become a neutron star. That has a diameter, so it has a binding energy. What is that binding energy relative to the original binding energy, or the original gravitational potential energy of the nebula that created it? There's a difference because some of the mass is ejected. That difference is the gravitational potential energy that generated the sunlight over the lifetime of the star. Rewind it, listen to that again because that's huge. I just gave you 4 years of research all summed up in like a paragraph. The difference in the binding energy of the resulting dwarf or neutron star, the difference in that binding energy compared to the gravitational potential energy of the nebula that created the star, that's the gravitational emergy of the sum total sunlight emitted by the star over its lifetime. And the ratio of those two, the ratio of that gravitational emergy to the solar output over its lifetime, is the gravitational transformity of sunlight. That's how it should be calculated. But I didn't have the data, and I'd already published this paper, and I didn't want to go back and do it again. So, but that's the future answer. Okay, so the GB we use, they just take kind of an average. They say instead of 12.1 or 11.6, they say it's 12, which isn't quite an average, but it's a nice round number to use. Solar equivalent joules, not Emergy joules. Okay, so now we move on to chapter 4. Chapter 5 is just a conclusions chapter. The Emergy of the crust. So you have the Emergy of the planet divided by the mass of the crust, and that's material quality. So that's called specific Emergy. Specific Emergy is the same thing as transformity, it's just for mass instead of for potential energy. Transformity is the Emergy per potential energy. Specific Emergy is the Emergy per mass. They are linked together by what's called specific exergy, joules per gram. So this, you know, when we say calories, that is specific exergy. Calorie is just another unit that's similar to joules. Calories per gram is a specific exergy. I could convert calories to joules and say how many joules per gram is this food, how many joules per gram is lumber, how many joules per gram is iron. Iron has chemical potential energy. All resources that have Emergy have a transformity and have a specific Emergy. Even sunlight. Sunlight has mass. Even wind, because wind has mass with the volume of air that's being moved. All things that have specific Emergy have transformity. Even the crust has a transformity. They have to, by definition. If it has Emergy, it has potential energy. If it has no potential energy, it has no Emergy. If it has potential energy, it has Emergy, so it could have a transformity, and it can have a specific Emergy. This is the biggest contribution I give in this chapter, because it's never been specified. So here are the 3 equations that lay it out for you. You can look in the paper for the proof of it. So when I do the Emergy of the crust, I don't count the oceanic crust. There's reasons for that, because the continental crust is 10 times more massive, 5 times older. It's compositionally different. It's less dense. And it's made, that's kind of redundant. It's made of granites versus the ocean crust is made of basalts. The ocean crust is very young, and it's not as massive. So even if I did count it, it doesn't really change much. But when we're counting the average age of the crust, we're really looking at continental crust. And we assume that the baseline of the planet is constant, even though over the generation age of the crust, which is about 2.5 billion years, the baseline's changed. The sunlight is much more intense now. It used to be about 70% of what it is 2.5 billion years ago. You know, the tides have been different, but we don't really know how the tides have changed. The tidal record's kind of skewed. We don't exactly know how deep heat's changed, and so we just assume it constant. But that would be an easy thesis. Easy thesis. just do a lit review on how sunlight, how tides, and how deep heat has changed. The radionuclides are easy to calculate because they have a half-life, so you just go back in time. That's actually super easy. And then you just apply the method that I just gave here, and that's a master's thesis, no problem. Take 3 months. There's a diagram of the crust. Get the 3 inputs because I combine radionuclides and relic heat. Concentrates average crust into these more ore deposits or concentrated minerals. The tides erode those minerals, and so does sunlight because it generates wind, and wind erodes things, ocean currents, and things like that. And then the ocean, yeah. And so things erode, they become ocean crust, or some of the ocean crust subducts. The ocean is actually draining into the mantle. Did you know that? That the ocean is slowly draining into the mantle. That there's about 4 volumes of ocean inside the earth of water. Yeah. True fact.
How fast?
What?
How fast?
How fast? Probably about an ocean per year. No, I'm just kidding. Well, here, I'll give you an idea because I don't know specifically, but the entire volume of water of the earth used to be in the atmosphere. When the earth was formed, it was like 5,000 Kelvin. Iron was in the atmosphere. And after a few thousand years, iron rained from the atmosphere. That's where we get banded iron belts. And then probably after a few million years, the atmospheres rained all the oceans out of the atmosphere. So when the earth formed, the pressure at the earth's surface was about 95 times what it is now. You would be crushed by standing on the surface, let alone you combust. But if you didn't combust, you'd be compressed. And that's because the entire weight of the oceans were in the atmosphere. So somehow, between 4.5 billion years ago and now, it went from being 0 volume of oceans in the mantle to now 4 oceans in the mantle, with 1 volume of ocean at the surface. It's slowly draining. It will never be completely drained, because in about 500 million years, the sun will be so bright that the oceans will evaporate again. So if we haven't moved to Mars yet, then we're done for, probably. But in 500 million years, who knows? We could evolve into, like, very heat-tolerant birds or something. I don't. Who knows? I need to cut that part out. Okay. Or maybe they learn something if I keep it in. So, 2.5 billion. Here's the equation: 2.5 billion years times the baseline divided by the mass of the crust. You can check the units for yourself. That gives you how much Emergy per gram of crust. So you might ask yourself, if you're really sharp and keeping up, well, this baseline here is solar equivalent joules, but Chris, over here is specific Emergy. That's not, is that units of equivalent joules? No, because the equivalent joules, once it's used up, once it's referred to in the past tense, it's Emergy. Emergy is in the past. Emergy doesn't exist now. Emergy is the Emergy that was used. Emergy is the potential energy that was used. It's gone. It's not available anymore. So when we account the baseline in something, it becomes Emergy. When it's the baseline, it's equivalent energy. When it's in something, it's Emergy. It's my invention. The whole point. I'll go ahead and explain this part. You might want to read the document if it's confusing, which it probably will be. Basically, I didn't compute the... Let me get some water. I didn't compute the chemical potential energy of the crust. I took it from other authors. The Valeros. Shout out Alicia Valero. Thanks for helping me out. And so they provide the Gibbs free energy of every mineral in the crust. 99.9% of the crust. There's a few minerals they don't do. And they also provide the chemical potential energy of the crust. So I make transformities for each crustal mineral based on both. Because there's some questionable things about the chemical potential energy. For instance, some of them are negative. But I can't have a negative transformity. So what do? Do I take the absolute value of it? Well, I could. But that seems a little unfair if they're negative. And they don't even like the Valeros don't like that there's negative chemical potential energies. It's just an inevitability of how they modeled it. And it's the best model because in other models, there's many more negative ones. Or in some cases, the models don't, their composition that they're assuming looks nothing like the actual crust right now. So they're basically just making up a crust. So the Valero's model is the best, but it's undesirable to have negative chemical potential energies. And you can look at their document for a better explanation of it, because I didn't make it. I go with the Gibbs free energies because that's how we use rain. That's how we account Emergy of rain, is the Gibbs free energy of ocean water versus the Gibbs free energy of fresh water in the atmosphere. And that difference is the potential energy of fresh water. So I do the same thing for the crust. There's a Gibbs formation energy of average crust, of a mineral at average abundance, and there's a Gibbs free energy of the mineral at concentrated abundance in an ore deposit. And that difference is the potential energy of the ore deposit. So that's the one I go with. And I only account the mixing term, which is the difference, I just explained it. That is mixing exergy. Mixing exergy is the difference between Gibbs formation energy at the concentrated state and Gibbs formation energy at the base state. I do these two other methods that deal with chemical exergy and average chemical exergy of the crust. So the average chemical exergy of the crust is I don't look at each mineral specifically. I just say, well, each mineral has a chemical potential energy. And if I add them up for every mineral in the crust, I have a chemical potential energy of the whole crust. The emergy of the crust divided by the potential energy of the crust gives me the average transformity of the crust, which is useful conceptually, but it ignores the uniqueness of each mineral, which is undesirable. It gives every mineral the same transformity. Iron has a different transformity from cinnabar, mercury. It should. And then I already said chemical potential energy isn't desirable because there's some negative ones. So I went with Gibbs formation energy. I have some results later that I'll show, but I'm going to ignore the chemical exergy ones. I'm just going to talk about the Gibbs. And then here's the Emergy accounting of uranium, because now we're getting into the economy of the U.S. The U.S. mined some uranium. In Chapter 2, I calculated the transformity of uranium. So the transformity times all the uranium gives me the Emergy contribution of uranium to the economy. Never before calculated. I also do a coral reef model because in the Emergy, so we talked about the Emergy to dollar ratio. So you have the Emergy of the economy and then all the money of the economy. And the ratio of the two gives you an Emergy per dollar. The number one biggest contributor of the Emergy of the economy is limestone. 25%, roughly. So about half of the Emergy of the nation is non-renewable resources. There's some renewable stuff like wind and tides on the shores and whatever. And there's some imported Emergies from other nations. About half of it is local, non-renewable. I'm just recording a quick presentation real quick. And so half of the non-renewable resources were limestone. But it was another hugely vague value, you know. So I go back and I say, what's the Emergy of a coral reef system? And that's here. So it used to be 9.5 E9, now it's 1.7 E9. So I greatly reduced that. Another table, you don't need to look at all those points. Shouldn't have a table like this in a presentation. So that's everything I just showed. Half of the Emergy of the nation was non-renewable, and half of that Emergy was limestone. So about 25% of the Emergy of the nation was limestone. So I changed that. Here I'm just looking at trends. You know, we assume that is a rare. If an element is rarer, it should have a higher Emergy value. The only one that does that is the Gibbs method, so I'll go with the Gibbs method. And so, like I said, I'm not going to talk about the chemical exergy results. Basically, what you see here, if you ignore the results on the right and only look at the ones on the left, the top left does everything new in that there's a new limestone specific Emergy, there's a new uranium or nuclear Emergy, and I update the average specific Emergy of the crust because I have a new baseline, I have a new mass of the crust, that's just new data. So with those three updates, that's the top left diagram. Everything's pretty dwarfed by fossil fuels. If I go to the bottom left diagram, because we're ignoring the two on the right, it's those three updates I just said: new limestone, new crust, uranium. But then I also change how I account the crust. It's no longer, if it's twice as concentrated, it's twice as much Emergy. I use that Gibbs method that I just talked about, the difference in formation energy at the base state from the formation energy at the mine. That's potential energy. What's the transformity of that? And then I count that for the main minerals of the U.S. economy. And it's a tiny, tiny sliver. It makes it really, really small. You can't even see it. It's insignificant. I'm not saying it's the best method. 1,000 years from now, we might have a better method. But what I would say is that the energy of fossil fuels is greatly overestimated. And I don't do a lit review of that in this dissertation, but I could explain why. If you have questions about that, you just send me an email. But that should be looked at too. That's a whole new dissertation to look at the fossil fuels. So that's the end. So the outlooks for the future include fossil fuels in a crustal model. The generation time of fossil fuels is hundreds of millions of years, and that should be included in the crustal model. Other things that occur on thousands of years, like groundwater, that shouldn't be included in the crustal model. There's a woman who came out with a method in the 70s called her name's Martha Gilliland. I didn't have a chance to include her method, but she has a really interesting method for computing the Gibbs formation energy of the crust. According to fresh water erodes the crust, and the difference in Gibbs formation energy of the ions floating in like river water from the formation energy of the bedrock, that difference is the potential energy of crust. I think it's brilliant. I just didn't have a chance to include it, so that should be looked at. Also, a mineral method that the transformity changes as specific energy changes. As I formulated it here now, the transformity stays constant as specific energy changes, which is incorrect. It's just straight up false. But it's better than what it was, which was there was no transformity. They had a specific energy of crust, but no transformity of crust. It was just not regarded. So here I'm including transformity, but it needs to be modeled in a way that transformity changes as specific energy changes. So look at the document so you can see the actual equations. And then also there's something called geopotential of crust. Mountains. There's a gravitational potential energy of the continents over the ocean. The higher you are, the more gravitational potential energy you have. That should be included because the baseline didn't just create the crust chemically. The baseline also created the crust elevationally. And then there's this thing called comminution potential energy, which is a rock. Basically, it takes energy to break apart a rock because it's holding itself together, and that's different than a mineral. It's comminution. Comminution. Those are all things that should be included. Outcomes. First ever nuclear Emergy, an evaluation of that. So now we have Emergy values for nuclear isotopes. Generalize the baseline. There's this thing called gravitational transformity, which is a forward calculated transformity. There's a Chinese scientist, his name eludes me right now, but he did something along these lines, but this is better. And the first ever understanding in the Emergy science is that there's a difference between relic heat and radiogenic heat inside the Earth. The proper understanding of the tides is that the Earth is spinning. I don't think I even went into that. The Earth is spinning and the Moon is dragging mass on the Earth. The Moon is dragging behind the rotation of the Earth. And so it's despinning the Earth. The Earth is slowing down because the Moon is dragging it, dragging the material on its surface. That's what generates the tides, is the Earth's rotational kinetic energy. Every mineral has a specific energy and a transformity. That's never before been done. I count nuclear energy in the U.S. economy. That's never before been done. And I do a biogenic energy evaluation of limestone, which is huge. That's a huge contribution. That one and the nuclear energy values are probably the two biggest contributions of this dissertation. And these are the publications I got out of this. And there's Dr. Brown at his retirement party. My beard is bigger. And these are just an example, you know, when we have our brainstorming sessions in systems seminar and we draw a bunch of diagrams on the chalkboard. So, you know, over the years, I took pictures of them. Instead of trying to draw them down, you just take pictures of them with your phone, and here's a couple of them. So, I think that's the end. Yeah. Any questions? Nothing? Did I put you to sleep yet? No?
That was amazing.
Cool. Awesome. All right, that's it, guys. If you have any questions, you send me an email, devilbus.cd@gmail.com. I'll put a link in the YouTube below the YouTube video. And also, when the dissertation comes out and is published, you know, it'll be open source and public, so I'll post a link for that too. All right. Namaste.